speaker after the break, Sterl Phinney, who speaking on enhanced and imposter defense. And I guess you're claiming the M conference loyalty reward. I think maybe that should be earned with exceptional interest.
Okay, well, I'm Sterl, the R and the L. There'll be a quiz for the East Asians afterwards, but otherwise it's easier to pronounce. I'm normally at Caltech, but this year I'm being Dutch on sabbatical and having a great time. So I guess my excuse for being here, presumably the reason I got invited, is a long, long time ago I predicted this T to the minus 5/3 in a long, beautiful paper on the starburst history of the Milky Way, the problems of star formation at high densities, lost cone tidal disruption rates, tidal stripping of giants, and all anybody remembers is the 5/3. So it's a warning for the young people in the audience when you write long, beautiful papers. Okay, so I want to, we've heard this morning about sort of the baseline tidal disruption event rates of stellar dynamics of spherical star systems with a black hole in the middle. And the rate depends on essentially diffusion into the lost cone on scales. Typically, the dominant scale is sort of typically around a half a parsec for Milky Way-like galaxies, and that's sort of well inside the radius of influence. For the Milky Way is a few parsecs. So the rates are then sensitive to the slope of the cusp, and I'll come back to that. I think a lot of people use rather generous cusps and even ridiculously generous cusps. And then I'll say a bit about enhanced tidal disruption rates. One case is, that I'll spend a little time on, is the case of having two black holes in the center, and then we'll talk about what happens if we put gas in the middle. So here's the gas in the middle. So in this case you have more gas, and in this case you have more black hole. So this is lots of black hole and not very much gas, and this is lots of gas and relative to the mass of the black hole. And you get enormous amounts of star formation in this corner and enormous amounts of inflow, and up here you get little inflow and little star formation. Okay, so let me talk quickly about the black hole binaries. This has been done many times. I think the first calculations was by Chen and Madao, who created a very steep star cluster, plonked two black holes down in the middle of it. There was an enormous shredding. If you create a black hole in the middle of an equilibrium star cluster, and you create two, it's even more exciting. The calculations that my students, Chris Vague and Nate Bode, did, we surrounded a primary by an equilibrium stellar cusp, not a non-equilibrium stellar cusp. With the Danon model, we chose Bacall-Wolf and 1.5, and you'll see later why those two numbers are special for star clusters, if you don't already know. That's in contrast to the Chen, who chose 1.5 and 1.75, so very steep r to the minus 2.25 clusters. And then we allowed a second black hole to spiral in by dynamical friction, starting at large radii, and self-consistently spiral in at the rate set by the ejection of the stars in the usual stellar dynamical way. The bound cusp, you'll notice that the mass of the cusp scales as the mass of the black hole to the 1/2 power for the usual m goes as sigma to the 4th relations. So we actually used a fit from Merit that has a 0.55 instead of a 0.5, but doesn't matter very much. And then the tidal disruption rate for main sequence stars, that depends on a tidal disruption radius compared to this cusp radius that scales, again, changing rather weakly with the black hole mass and rather more sensitively with the stellar mass. So we put the stars and the black holes in the potential of the cusp, included the general relativistic precessions and gravitational radiation losses, because we were interested in MREs as well. We used a symplectic integrator with a fictitious time variable, so it's extremely accurate even for 0.59 eccentricity orbits. And then in contrast to some earlier claims, so this shows radius versus an angular momentum relative to the circular angular momentum. This is the famous Kozai wedge. There were some early claims that the dominant effect feeding things in was Kozai perturbations. Of Clearly, most of the things that are tidally captured were not sent in by Kozai. They're just sent in by complicated three-body orbits, Newtonian three-body orbits, of the two black holes and the single stars as test particles. So here are the rates. The general result is that roughly 10 to the minus 3 of all the stars in the cusp, so that's roughly 10 to the minus 3 of the sum of the two black hole masses, with this definition of the cusp as the mass at the influence radius. So about 10 to the minus 3 of them are tidally captured. There's quite a weak dependence on M1 and on mass ratio. The time scale depends on the mass ratio, but the number that get captured doesn't depend on the mass ratio much. And the time over which you get this, obviously this is an enormously enhanced rate. That's a capture of 10 to the 3 or 10 to the 4 stars in the time scale, which is roughly the time for the black hole to spiral in from the influence radius to the stall radius, where it's ejected enough stars that no longer, stellar dynamics are no longer shrinking the orbit. So here are two representative simulations, one for 10 to the 6 solar mass black hole and the other for 10 to the 8, sort of the two ends of the tidal disruption range that are of interest. Here is the time scale for the enhancement rate for mass ratio of 0.3, so that's 3 10 to the 5 and 10 to the 6 solar mass black holes. And here 0.1, so 10 to the 5 and 10 to the 6, so it's a little bit longer because the spiral in is slower for the higher mass ratio. And the peak tidal disruption rates in this case are about 1 every 300 years, and in this case 1 every 20 years. So remember, that's in contrast. Chen et al. Were getting several per year by these incredibly steep cusps with the black holes created in the middle of a non-equilibrium star cluster. So if you can do that somehow, you could get higher rates, but I think these are probably more realistic cusps and realistic in-spirals. So this again just shows graphically the rate for 10 to the 8, 3 10 to the 7, 10 to the 7 to show how the rate drops. And the rate is dropping basically because it's the mass of stars that are being captured is scaling with the mass of the black hole, so that's why the rate drops. And also the time scale changes a little bit as well. And so you can see that typically we're getting rates of order 1 every 10 years to 1 every 100 years over a time scale of a few million years for the Bacall-Wolf type cusps. Okay, so let's try to put this in cosmological context. So that was all stellar dynamics. We were ignoring all the gas. Is that the right thing to do? So here's the latest ERIS-BH simulation of the Milky Way from redshift 4 to 0, and this graph shows the black hole and the masses. There are 4 black holes that merged during this time. So the total is this top yellow curve, and the little steps are where the 2 black holes actually merge. And you see that at least this, which is carefully designed to be a reasonable simulation of the Milky Way from larger scale simulations, hasn't had any significant mergers since a redshift of 1.2. So over the last 5 billion years, the Milky Way hasn't gotten any significant new binary black holes. So we would be, if this was the typical tidal disruption rate, then everything I've just told you in the last 5 minutes was irrelevant for the Milky Way. And you look at the gas accretion rate, and since redshift 1.2, so the whole local universe, the gas accretion rate has been about 10 to the minus 5 solar masses a year from the stellar winds and little bits of stuff coming in, hot phase Bondi accretion, so 3 10 to the minus 4 of Eddington. So this gas phase capture is just making the very low luminosity ADAF in the center, roughly what we see. On the other hand, this simulation probably doesn't allow a starburst producing 100 O stars 10 million years ago. That wouldn't have been predicted in here. This is the total star formation rate in the galaxy times 10 to the minus 3. So you can see the total star formation rate is a few tenths of the solar mass a year, maybe a little low for the Milky Way. And so if this was realistic, then stellar dynamics is the whole story. So one other thing, since I just threw this in because a lot of people have been saying, oh, well, we can fix everything by tidally disrupting Jupiter and 0.1 solar mass stars. Let me just remind you about mass segregation, that if this was the story, if there was no continuing formation, these are 2 Fokker-Planck simulations from Brian Murphy and collaborators. So they created stars with the Krupa IMF. This one is a black hole, sort of like the Milky Way. After, at the current time, it's 4 million solar masses, and this one's 10 times heavier, 4 10 to the 7. So if we look at this one first, there are lots of 10 solar mass remnants of the black holes, which dominate the mass density in the inner parts. The stars, the main sequence stars, remaining main sequence stars, which actually dominate the density, are the 1 solar mass stars. So these are the 0.25. So they're about 1/4 the mass density and about equal numbers in number density. But of course, these have a larger tidal disruption rate. So the tidal disruption rate actually is dominated by the 0.95 solar mass stars because the low mass stars have been pushed out. For the higher mass black hole in this case, it turns out that it's actually the 1/2 solar mass stars which are dominating the rate, sort of being set out at the radius of influence. So the 1/2 to 1 solar mass stars are sort of winning over the 0.2 solar mass stars in this equilibrium. So just remember, what you create is only relevant as the IMF if you look in much less than a relaxation time. The relaxation time is typically a few billion years, so you probably wouldn't expect things to be dominated by the low mass stars, in my opinion. Okay, now this assumes a Krupa IMF. You may know that Nyakshin and Sunyaev in 2005 pointed out that in the center of the Milky Way we have of order 100 O stars. They're less than 10 million years old, so if each one of those should be accompanied by 100 1 solar mass T Tauri stars shining an X-ray for 10 million years, and there aren't any. And so they argue that the IMF must be much flatter than this, which will only, if the last starburst in the center of our own galaxy was typical of what happens in starbursts and nuclei, star formation at the very high densities here, very high optical depths. It's different than the local ISM. Maybe that, if that's a general top-heavy IMF, then there'll be even fewer 0.2 solar mass stars than predicted in this, which just has a normal interstellar medium IMF. Okay, let me spend a little time. I think this E plus A business is quite interesting, so let me give a slightly different take on it than was given earlier this morning. So as you heard from my ear, originally 2 out of 3 of the PTF nuclear optical transients were in E plus A galaxies, and yesterday we heard that 6 out of 6 of the other ones are in E plus A-ish galaxies, shall we say. So let me tell you a little about the history of E plus A galaxies. So the first ever spectrum of the fuzz around a quasar was taken by Borosin and Oak in 1982. And they got a spectra of the fuzz around the quasar 3C48. That's quasar number 2 in the history of quasars, remember? So this was the first time anybody got spectrum of a fuzz. At that time in 1982, there were great arguments about whether quasars were actually in galaxies or whether it was gas disks or what the fuzz was. They got the spectrum. There's the spectrum, H gamma, H delta, H8, and so on, right? And so they pointed out that this was an underlying galaxy, is a spiral in which a massive star formation burst was triggered at least 10 to the 8th years ago. It's a classic E plus A spectrum. Okay, if you look at the recent history, 2015, here's all the study of the spectra of the fuzz around all the Sloan quasars at redshift less than 1, and they find that almost all of them are basically post-starburst E plus A-ish spectra, stellar ages around 1 gigayears. And the post-starburst name, I think, is generally agreed to be a bit misleading. It means you need star formation, and then you have to stop it very suddenly. You don't actually need a burst, but you have to stop it very suddenly so that you can eventually get the light dominated by the A stars without having B stars contributing extra blue light. So that's the crucial step. So you have to really drop the star formation rate by a factor of 100 fairly quickly over a time scale of less than 100 million years or so to get these type spectra. Okay, so this is the majority. This is 191 quasars redshift less than 1, and the majority of them have these kind of spectra. So you can now ask the general class of these galaxies. So this class was first invented by Dressler and Gunn in 1983, the year after Borosin and Oak found the quasar had these spectra. And they were looking in a cluster around the radio galaxy 3C295, which is how you got high redshift galaxies in those days. And in this cluster around 3C295, it's rather remarkable. 10% of the cluster members are Seyfert galaxies, and 10% of them are E plus A's. If you look in the Coma cluster, 0 out of 200 galaxies are E plus A's. And if you look in their random sample of 1,200 cluster galaxies they'd gotten spectra of, only 10 of them had this, of which 3 were in this cluster. Okay, so these E plus A galaxies and Seyfert galaxies seem not only to be in the same thing, they also are great friends, even when they're not. So the current status is, again, from the Sloan survey, looking specifically for galaxies with this type of spectrum, but now not in Seyferts or quasars. The space density is actually comparable to the space density of quasars. The specific star formation rate, as I said, you have to drop it really dramatically, so the star formation rate per unit stellar mass is about a 10th to a 30th of that in the Milky Way, and that's how you create these type spectra. So the other recent term for these kind of galaxies, some of you may have heard about the green valley between the red and the blue type galaxies, the early types. So if you plot color versus stellar mass, you can also plot color-color diagrams. They're basically all the early type galaxies, and this paper, Sherwinski et al., again, was going through Sloan and then using the galaxy zoo, actually classifying these morphologically, so these really are early type in the Hubble definition of the shape, and these really are disk galaxies in the shape, but the colors reflect that. So the early type galaxies, which tend to be red, they're the disk galaxies, which tend to be blue and somewhat lower mass, and then there's this rare patch in the middle, and this is where the E plus A's live. And these galaxies are so rare in this patch that in fact you can't say that all spiral galaxies gradually turn off their star formation rate and end up here, or you get way too many in here. So it's only like 1/100th of them that actually have this sudden stop of this star formation. So in the last 5 years there's been great, many of you heard about AGN feedback and mergers quenching star formation and so on. So the idea is that something, rare events suddenly quench star formation in galaxies which evolve up to these early type galaxies and are responsible for these rare E plus A post-ish, post-starburst galaxies. So here's a little more just showing the star formation rates that you need in order to get up into this, that you really have to turn off the star formation rate in less than about 100 million years in order to end up in this region. Otherwise, you sort of march off in this direction or march off too far to the blue instead of moving up in the diagram. Now, the question of how this actually happens, one popular story is that you have AGN feedback. On the other hand, the AGN feedback is a bit problematic because we saw most AGNs actually have E plus A spectra, so while the AGN phases go just turning on, you might think, how did it eject the stuff a billion years ago, right? So I think the more popular story is one, I guess first proposed by Hopkins, that this shows in his simulations the star formation rate, and this shows the black hole accretion rate, and here's a few 100 million years. And the reason for that is that the black hole accretion rate depends on the density of gas in the very innermost parts, and the star formation rate is averaged over the whole galaxy, a few kiloparsecs. And it takes a long time for the stuff to drain from the outer parts into the inner parts. So by the time you've drained the gas and formed it into stars in the outer parts of the galaxy, there's still some dregs left in the middle, and those dregs are what allow the black hole to keep accreting. It may have actually, in some simulations, you can get it to be accreting during the starburst as well, but then it's buried and it's an ultraluminous IRAS galaxy and you don't call it a quasar. So by the time you see it as a quasar, all the mess is cleared out from the outer parts and it's just the dregs coming in that are still powering the inner parts of the gas. And this shows the star formation rate and the black hole accretion rate defined in the inner 10 parsecs of the galaxy, or 20 parsecs, I guess, in this region. Okay, so some implications for the TDEs. I think the most interesting implication is that looking at the connection between these E plus A-ish galaxies and the AGN is that it indicates that the star formation in the outer parts of the galaxy is turned off, but there still is currently or very recently been lots of gas in the nuclear region to either feed the black hole or cause nuclear star formation. So I think there's interesting possibilities for enhanced rates. and imposters, as I'll mention briefly. One is that if you have a significant amount of gas, by significant this means like more than 10 or 20% of the mass of the black hole in a disk on the scale of subparsecs, then the disk is self-gravitating on those scales, it clumps up, gets eccentric instabilities and so on, and so you can scatter any stars which you made around there in the disk, using the disk as the clumpy medium or the non-symmetrical m=1 mode to scatter the stars. And of course the large numbers of young stars that you would have here also might be supernova imposters that I'll discuss briefly in the last minute. So if you sort of work out again these enhanced rates, I think it's quite easy to arrange that the typical TDE is not in a typical spiral galaxy. And then again, because if it's associated with this young recent star formation, there could be significant numbers of 10 solar mass stars undergoing disruptions, which we might not be keeping at the moment because they'll be slow, right? They're 100 times lower density than 1 solar mass stars. So here's the complicated formula to explain why that's true, right? We've heard that spherical stellar dynamics gives a rate of, I put 6 10 to the minus 5 as the geometric mean between the old 2 10 to the minus 5 and this morning's 2 10 to the minus 4. Since a redshift of 1, 5 billion years, you can arrange that by having 0.1 per year for a few million years, either by the binary black holes or scattering young stars and disks. And that means that half of the TDEs are from this class and half are from that class, so this is a significant contribution to the rate. So these would be the E plus A potentially. Let me skip over the star formation in the galaxies and just leave you with the imposters. So as we heard, the TDE, optical TDEs we see are 10 to the 51 ergs, about a solar mass, several thousand kilometers a second. You tell that to an astronomer and there's a knee-jerk reaction, supernova. Now, of course, the supernovae don't have, the typical ones don't optically 10 to the 51 ergs because of adiabatic expansion, so you have to reconvert the kinetic energy to thermal energy on the right time scale to get months or year time scales. But in the centers of galaxies, I think that's actually not hard to arrange. So the recently discovered magnetar in the center of the Milky Way has a ratio of rotation measure to dispersion measure of 2.5 milligauss, dominated by the 0.1 to 5 parsec. That's a magnetic pressure more than 1 million times larger than that in the interstellar medium, local interstellar medium. So, so that means that neutral and photoionized gas density in equilibrium with this will have densities of 10 to the 5 or 10 to the 9 per cubic centimeter. And if you blow up a supernova in this sort of material, it goes directly from the free expansion phase, skips the set-off phase, goes immediately into the radiative phase in less than a year. So T to the minus 5/3, I think, remains an interesting puzzle, but I think it's worth thinking a little bit about whether some of these old Turlovich ideas of trying to make AGNs by supernovae in dense media might actually be happening. Maybe not all the quasars, but some of the interesting events we see might actually be these. I'll stop there.
Questions for Sterl?
At some point you mentioned the simulation of Milky Way and its age, right? And the accretion rate of the black hole was suggesting the rate of 10 to minus 4 as unit number. But isn't it that the observations of Sagittarius A star suggest rather 10 to minus 7 and minus 8?
So that's the accretion rate, not the luminosity, remember. So at those accretion rates below about a hundredth of a Eddington or maybe a few thousandths of Eddington, right, the efficiency becomes very low. So the luminosity, the gas accretion rate in the center of the Milky Way is thought to be about 10 to the minus 5. The luminosity is 10 to the 36, 10 to the 37 ergs a second.
There's also the question of how much starts on the way in and then gets plucked out.
Yeah, this was purportedly a Bundy rate coming in, but I think that rate, depending on your details of your views about ADAFs, I think that could be consistent with the luminosity
So
of
I
it.
would support Julian's point because the 10 to minus 7 is I mentioned, it actually comes from the rotation measurement, and this tells us about the rate of the gas density in the nucleus of accretion rate, not the level of N-minus select, which may be much lower than the Pauling accretion rate.
Yeah, but sorry, the rotation measure doesn't tell you the gas density, you
Well,
mean?
talking about
Yeah.
a sort
Or
of
the-
high-frequency radio looking at that
Yeah,
star,
yeah,
and that
yeah.
indicates a much lower density close in.
Yeah, no, yeah, sorry, I was talking about the accretion rate of 0.1 parsec or something, yeah. That's right, yeah.
So the point you mentioned about whether we really need a starburst or just quenching, that's a good point, and we've actually started testing that. So we're running several population instance models on the hosts of TD, and at this point they do seem to be more consistent with a starburst than just a regular starburst quenching. So that's
So they, I mean, are they then different in a subtle way from the generic green valleys, which
I think they
say-
should
does it
be,
mean?
but yeah, we're really trying to figure out where they are in phase space. More
Because I guess that really depends on the,
Yeah.
yeah. So that, I guess that depends on making sure you understand the giants, because I guess the Lieber arm between the A stars and the older ones that will set the starburst will be sort of in the red or infrared.
Are there estimates of the black hole masses in those 2%?
Oh,
From the host?
yeah, so the quasar ones, of course, are, depending on the luminosity of the quasar, they're the usual 10 to the 7 to 10 to the 8 for the Seyferts, and 10 to the 8 to 10 to the 9 for the quasars from the M sigma and H alpha line width estimates and so on. In the ordinary in the E plus A's that are not AGN, there are about half of them are AGN and the other half are not. Some of them sort of show liner spectra, and the usual arm waving suggests there are a few 10 to the 7, 10 to the 7, but I'm not sure. Liners, black hole masses from line widths are a bit dodgy, so I don't know how much to trust them. Oh, and the stellar sigma, yeah, they're again, there's a range, but the predictions you would get from the stellar masses are a few 10 to the 7 on up to several 10 to the 8.
I just have a question of your sponsors here. Do you expect to get a gamma ray counterpart?
No, the interest, well, you might get gamma rays. The one interesting thing about these is that in the high density regions, because you go directly into the radiative phase from free expansion, you have shocks that are at 5 or 10,000 kilometers a second, so you actually expect hard X-ray transients, which would be an interesting signal to look for, I think.
Yeah, on that note, on the imposter, do you expect also more extreme UV, which is now being used as really a diagnostic to rule out any stellar explosions?
Well, I think these probably, I wouldn't expect a lot of UV. As I said, the most of the cooling luminosity comes out actually in the X-rays, sort of KEV X-rays. And there will be some UV as it cools down, or if the X-rays get reprocessed, but it's not sort of a fundamental part of it. You can then use the X-rays photoionize and produce optical emission in the bubble around it. But intrinsically, it's not UV.